just finished giving you an overall idea about the different ways in which glucose structure is shown. Now the first one that I'm going to discuss in detail about is the open structure of the glucose. The evidences for the open structure of glucose. What are the reasons for the development which lead to the conformation of the open structure of glucose? Now for that, the first thing they came to know was the glucose has the molecular formula of C6 H12O6. Molecular formula of glucose was found to be C6H12O6. And the second experiment which they did was when glucose was treated with, or when it was heated with hydrogen iodide, it gives N-hexane as the product. Okay, now glucose has the molecular formula of C6H12O6. Now this, on prolonged heating with hydrogen iodide on prolonged heating acts as a very good reducing agent or strong reducing agent. Now this reducing agent reduces all the carbonyl and the hydroxyl groups to alkane group. So therefore N-hexane was produced. N refers to the carbon atoms which are arranged in a straight chain. So 1, 2, 3, 4, 5, 6. 6 carbon atom in a single straight chain. This will be CH3, then you have CH2, 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 CH3. Now from this, it was concluded that the carbon atoms, or the 6 carbon atoms present in the glucose, is in the form of straight chain. From this, it is concluded, or it was concluded that carbon atoms are in a straight chain. So this is the experiment from which it was found that carbon atoms are arranged in a straight chain. Now the next experiment was when glucose was treated with hydroxylamine. It forms oxime. Similarly, when it was treated with hydrogen cyanide, HCN, it gives cyanohydrin compound. Now formation of these two products, oxime and cyanohydrin compound, indicates that it contains a carbonyl group, shows presence of carbonyl group. Okay, now let me give you the reaction for this. So the first one, that is glucose C6H12O6 on treating with hydroxylamine, that is H2NOH. This is your hydroxylamine. Now when glucose was reacted with hydroxylamine, it forms an oxime compound. Now how does that happen is, glucose can be written as C double bond O H, CHOH 4 times, and then you have CH2OH. Now this O with the double bonds with carbon atom will leave with H2 from the amine group in the form of water. Now this two will leave in the form of water, and this double bond is connected to this nitrogen atom. So you will get HC double bond NOH. And then you will have your CHOH 4 times, and then CH2OH. Now carbon with double bonds N is called as oxime, a compound containing carbon double bonded to nitrogen atom. So formation of oxime takes place when the glucose was treated with hydroxylamine. Now this happens only when the carbon atom contains a double bond O. This shows that, or this proves that carbon of the glucose contains a carbonyl group. Okay, then the next one is when glucose was again C double bond O H, CHOH 4 times, and then you have CH2OH. When glucose was reacted with hydrogen cyanide, what happens is again, this double bond will shift. O will have a negative charge, C will have a positive charge. Now on this, Cn minus will come and attack, and this hydrogen with the positive charge will go and attack the oxygen. So you will get a cyanohydrin compound. That is, this oxygen, carbon, will have a OH group, and then this Cn will come and attack this carbon. So H, and then, okay, let me write it on the top. OHCN, and the remaining CHOH 4 times, and then you have your CH2OH. Now this shows the formation of a cyanohydrin compound. So again, this will react only when there's a presence of C double bond O. So from this two reaction, or the formation of oxime and formation of cyanohydrin, indicates that glucose contain a carbonyl group, but we don't know yet whether the carbonyl group is aldehyde or not. So for that, the next experiment was done. Now in order to find out whether the carbonyl group present in the glucose is aldehyde or ketone, glucose, that is CHO, CHOH 4 times, CH2OH, when it was treated with bromine water, which acts as a mild oxidizing agent. Glucose got converted to gluconic acid, so where you have COOH, CHOH 4 times, and then CH2OH. This is called as gluconic acid. From the formation of gluconic acid, it is confirmed that the carbonyl group present is an aldehyde. That C double bond O is an aldehyde group. The reason for this is because ketone R C double bond O C R. In order to oxidize ketone, you need to break the bond between this carbon and carbon of this R group. So it's very difficult to break this bond by using a mild oxidizing agent. Only aldehyde groups get easily oxidized, because in aldehyde you have R C double bond O H. Now it's very easy to oxidize this hydrogen atom than this R. So therefore, whenever you treat aldehyde with a mild oxidizing agent, it gets converted to a carboxylic acid. So from this, it was confirmed the carbonyl group present is an aldehyde group. The next reaction that was carried out was when glucose was treated with concentrated HCl2, that is CHOH 4 times, and then you have CH2OH. When it was treated with concentrated HCl3, it acts as a strong oxidizing agent. And both the groups C1 and C6 got converted to a carboxylic acid group. So therefore, saccharic acid was formed in this case, CHOH 4 times, and then you have CHCOOH. This primary alcohol got oxidized to a carboxylic acid on treatment with a strong oxidizing agent. So from this, it was confirmed that there is a presence of primary alcohol in glucose. Okay, now the next reaction shows the presence of 5 hydroxyl groups. For that, acetylation of glucose was carried out with acetic anhydride in the presence of pyridine. Okay, let me write down the reaction for this. Glucose, that is CHOCHOH 4 times, and CH2OH. When glucose was reacted with acetic anhydride, that is CH3, C double bond O, O, C double bond O, CH3. If you remember the formula of acetic anhydride, it is CH3, C double bond O, O, C double bond O, CH3 in the presence of pyridine. It leads to the formation of glucose pentaacetate, that is CHO, CHO, C double bond O, CH3, and then CH2, O, C double bond O, CH3. This is 4 times. So you can see that 4 acetate compounds plus 1 acetate compound. So a pentaacetate, glucose pentaacetate, compound was formed when it was treated with acetic anhydride in the presence of pyridine. This shows the presence of 5 hydroxyl groups, 4 OH here and then 1 OH, total 5 OH groups. So because of presence of 5 OH groups, you got a compound which contains 5 acetate groups. So this confirms the presence of 5 OH groups. So it might be difficult to just remember the structure of this compound. So I will tell you how does the formation of this compound takes place. Now what happens is whenever an alcohol, that is ROH, is treated with acetic anhydride, that is CH3, C double bond O, double bond O, CH3, sorry, C double bond O, O, C double bond O, CH3, what happens is the O of the alcohol have 2 lone pair of electrons. Now what happens is this lone pair of electron with the oxygen atom will form bond with this carbon atom. For that, this has to shift. O will have a negative charge, carbon will have a positive charge. Now this will lead to the formation of R, O. Now O is connected to this carbon, and then this CH3, write it at the bottom, and then O with a negative charge, and then you have this O, C double bond O, CH3, and this O as 1 hydrogen atom. Since O is losing its lone pair of electrons, O will get a positive charge. Now in order to stabilize the positive charge on the hydrogen atom, oxygen atom, this hydrogen will leave in the form of H+. Now this negative charge will come back to form the double bond. Now carbon cannot have 5 bond again, so this will leave. And this CH3COO will combine with this and it forms CH3COH, and you get a product where it forms R, O, and then you have C double bond O, and then CH3. So this is the acetate compound. Similarly, in this case also, the OH group of the glucose, CHO, CHOH, 4 times and then CH2OH. This OH and this OH will react with this carbon, and this will leave, and this hydrogen will leave. This is how the formation of this product takes place, glucose pentaacetate. Now from this it is confirmed that glucose contains 5 hydroxyl groups. From all the reactions that glucose showed, it was concluded that glucose has an open structure. Now before that, I will write down the reaction that we just discussed in a very short way so that we can refer and then draw the structure. The first reaction was with hydrogen iodide. With hydrogen iodide, it was confirmed that carbon atoms are arranged in a straight chain. And with hydroxylamine, that is NH2OH, and hydrogen cyanide, it showed presence of a C double bond O group. And then the third was reaction with the mild oxidizing agent, that is bromine water, it showed the presence of aldehyde, of an aldehyde group, and with concentrated HNO3, which acts as a strong oxidizing agent, shows presence of primary alcohol CH2OH, and then with acetic anhydride CH3 C double bond O, O C double bond O, CH3, it confirmed the presence of 5 OH groups. Now let us draw the structure of glucose by referring to this. First, glucose has the molecular formula of C6H12O6. Now the first experiment with hydrogen iodide on prolonged heating with hydrogen iodide, it confirmed that glucose contains all the carbon atoms in a straight chain. So 1, 2, 3, 4, 5, 6 carbon atoms. Then reaction with hydroxylamine and hydrogen cyanide confirmed the presence of a carbonyl group, that is C double bond O, and reaction with mild oxidizing agent confirms that the carbonyl group is an aldehyde. Now the reaction with concentrated nitric acid shows the presence of a primary alcohol, which is on the 6th carbon atom. And then reaction with acetic anhydride confirmed the presence of 5 OH group. So you need to remember the position of the OH groups. This is the first, second, third, fourth, fifth, and the 6th carbon atom. On the 2nd carbon atom, OH will be on the right hand side, and then your hydrogen. On the 3rd carbon atom, OH will be on the left, and hydrogen on the right. And in the next two cases, you have OH on the right, and then hydrogen, hydrogen. Always, OH on the 3rd carbon atom will be on the left. Rest, OH will be on the right. Now, depending upon the position of the OH, you have two different types of glucose, that is D-glucose and L-glucose. That depends upon the position of OH on this lowest chiral center. Now in this case, the OH is on the right. If it's on the right, it is called as D-glucose. If it is on the left, then it is called as L. Now in this case, this is D-glucose. Now you will see that along with D, a plus sign is also indicated. So D plus glucose. D plus glucose in this case. Now D indicates the configuration of the OH according to the chiral center carbon, whereas the plus sign indicates the optical activity. It shows that the glucose rotates the plane of polarized light towards clockwise direction, because of which it will have a plus sign. If it rotates the plane of polarized light towards the anti-clockwise direction, then it will have a negative notation. The plus sign, or you can also use the term dextrorotatory, or glucose is also called as dextrose, because it rotates the plane of polarized light towards the clockwise direction. So that's about the structure that was concluded after conducting all this experiment. Tadi khari la wala na glucose la structure thida sumures tambo the open structure che dine cyclic structure che dine khari wala na Hemiacetal structure nani. Tada azu che di khari na open structure de khandis thatche me open reaction nani ba. Tadi na ma tambo reaction the glucose hydrogen iodide nyamdola chidu sambala khari tende la na khogi glucose de khari la glucose de na N-hexane la glucose. N-hexane la glucose samala N-hexane ki nano la khari na carbon sama straight chain ka la glucose samala and glucose nano la carbon glucose sama khari na sama khadu chain your list 1 2 3 4 5 6 and straight chain chi nano la any reaction with hydroxylamine the hydrogen cyanide nam the chidu samala 아니 거기 oxime form 체 hydroxylamine 냠도 oxime 체 hydrogen cyanide 냠도 cyanohydrin compound form 차이도와 되네 가리 병거라나 glucose 나로라 carbon 치기가나 C double bond O2 carbonyl group 체 carbonyl group 유나 마시 군이 react 마레스 되지네 carbonyl group 체 도서들네 하고와 다 디줄라 will reaction with mild oxidizing agent bromine water 냠도 치디 samala 가리 때네라나 carbonyl group yugo di aldehyde ratios karichina aldehyde tina mashi ko oxidize chai mare ketone di kadina mild oxidizing agent chinyam do oxidize chai mare kajina ketone ki nalo la c na c ni ki mala bond cha utwa aldehyde nalo la c na h ni ki bond chai le la with sabala aldehyde di le la utoni oxidize chai de chini carbonyl group yugo di aldehyde ratios ne hamore then reaction with concentrated HNO3 nyam do chidi samala ta di primary alcohol chiyar ba di ke acid lagure ta di acid lagure sama khari ta ho na di carbon di gama alcohol group chidis khari chenana concentrated HNO3 the strong oxidizing agent chidi samala di alcohol di khari lagure na acid lagure ta di yo ha poswa carbon thro yo ha posu aldehyde yo ha posu di yo ha poswa ta OH group di nga yo hande sawala na acetic anhydride ndo react chidi samala ko ge penta acetic compound chi form chaidwa dine ani also khari ha bole OH nga dos ani structure di dus thachre open structure di ta open structure jive gama chemba share di khari chemba shawala na OH di khawa ko chidi ne carbon niwa kana OH di khati na right lache ani dine carbon suba kana chidi sabala OH di khati na left kana che ani carbon shiva kana wala OH di kare right la di res dus che ta open structure la glucose type ni che ra tango di D glucose che ani yiwa di kare la na L glucose D glucose khati la na kisi OH di carbon ngawa kana yugo di labo eba chola yena and D glucose che kisi OH di labo eba chola yugo china ani ko kare che la na L glucose those chine D glucose L glucose lane ni hai. Okay, so this open structure of glucose is also called as Fischer structure. Okay, I'll write it here. Called as Fischer structure or Fischer projection. And this D and L notation, if OH is on the right, it is D. If it's OH is on the left, it is L. This notation was given according to the position of OH on the carbon atom in glyceraldehyde. In the case of glyceraldehyde, you have CHO, OH, H, and then CH2OH. Now in this case, if the OH is on the right hand side, it is said to be D, and it is again a dextrorotatory, and you will have the name of the compound, glyceraldehyde. Now D notation indicates the position of the OH. This plus sign indicates the optical activity of the compound. Similarly, if the OH is on the left hand side, that is COH, CHO, H and CH2OH, it is called as L plus glyceraldehyde. So this is about the open structure of glucose. Okay, now that we are done with the open structure of glucose, let us discuss about the cyclic structure of glucose. Now, what are the reasons that we came to know that glucose exists in the form of cyclic as well? The reason for that was the open structure of glucose, despite having free aldehyde group, it does not react with 2,4-DNB test or 2,4-DNB reagent. Skip space and does not form addition product. with sodium bisulfite. NaHSO3 sodium bisulfite. And the next reason was glucose pentacetate. Acetate does not react with NH2OH, that is hydroxylamine, to form enzyme. Now this two reason shows that the aldehyde group of glucose is not free. If it will free, it should react with 2,4-DNA reagent, it should react with Gibbs base, and it should form addition product with sodium bisulfite, but this did not happen. Also, the aldehyde group of glucose pentacetate does not react with hydroxylamine to form enzyme. So which means that the aldehyde group of glucose is not free and it is involved in cyclic formation. So that's how we came to know that glucose also exists in the form of cyclic structure. So let's go to the cyclic structure of glucose now. Okay, to know the cyclic structure of glucose, let us first write down the open structure of glucose. You have 6 carbon atoms, 1, 2, 3, 4, 5, 6. The last carbon atom is a primary alcohol. The first one is an aldehyde, and then you have OH, H, OH. The third carbon carries OH on the third carbon atom carries OH on the left hand side. Then you have H, OH, OH, H, and H. So this is the open structure of glucose. In this case, I have drawn the structure of D plus glucose. Now, what happens is this OH on the 5th carbon atom will react with the aldehyde group of the glucose and it forms a hemiacetal compound. So for that, let me first explain the formation of hemiacetal compound. So whenever there is a presence of aldehyde and alcohol, or ketone and alcohol, it leads to the formation of a hemiacetal compound. So whenever you have ROH and RC double bond OH, what happens is this oxygen carries a lone pair of electrons and this carbon will react with this oxygen. For that, this pi electron will shift, O will carry a negative charge and this carbon will carry a positive charge. Now on this oxygen with the lone pair of electrons will come and attack and you will get ROH. Now O will have a positive charge and this is connected to this carbon, and then you have O with a negative charge and then this R. Write this R at the bottom and then this hydrogen. Now what happens is, since O cannot have a positive charge, this hydrogen will leave in the form of H plus, and this H plus will go and attack this oxygen atom. And this results in the formation of R, O, and then you have C, OH, H, and R. Now you can see that this carbon atom carries a OR group, it carries a OH group, it carries one H, and this carries a R group as well. So such compounds is called as hemiacetal compounds. So hemiacetal formation takes place when alcohol reacts with an aldehyde or alcohol reacts with a ketone. In glucose also you have a hydroxyl group on the 5th carbon atom which will react with the aldehyde group of the glucose and it forms a hemiacetal compound, because of which it results in the formation of a cyclic structure. Now let me explain the formation of cyclic structure now. Now what happens is this O with a lone pair of electrons will attack this carbon atom. For that, this carbon have C double bond OH. Now, in order for this oxygen to come and attack this carbon, this will shift. O will have a negative charge and this carbon will have a positive charge. Now in the process, O will get a positive charge. Now in order to stabilize the positive charge, what happens is this hydrogen will leave and this H will come and sit on this oxygen atom. So that's how OH group is formed here. Now I will write down the complete cyclic structure. First, second, third, fourth, fifth, and the sixth carbon atom has a CH2OH. Now what happens is, this fifth carbon atom, the fifth carbon atom will form a bond with the first carbon atom through its oxygen, and this will have a OH because this O picks up the H plus from here, and you have your hydrogen, OH, H, and then OH, H, OH, and H, and then you have your H. Now this is the cyclic structure of glucose. You can see that this carbon consists of one OH group, one H group, and one OR group, and then R group. So hemiacetal is being formed. Now in this case, you can see that the OH on the first carbon atom is on the right hand side, therefore this is alpha. It is called as alpha D plus glucose. If the OH is on the right, OH on C1 is on right, it is alpha D plus glucose. If OH on C1 is on left, it is called as beta D plus glucose. So that's how you get two isomers of glucose based on the orientation of this hydroxyl group on the first carbon atom. So because of this reason, this O is called as anomeric carbon atom. And these two, alpha D glucose and beta D glucose, are called as anomers. Now if I write down the beta form of this, you will have OH on the left hand side, and then you have your H. 1, 2, 3, 4, 5, 6. This one will have CH2OH. And now this forms a ring with the fifth carbon atom through the oxygen. And you have your OH, H, OH, H, and then OH, H, and H. Now since OH is on the left hand side, this is called as beta D plus glucose. Okay, now these are the two anomers of cyclic structure of glucose, that is beta D plus glucose and alpha D plus glucose. Now let's move to the Hammond structure. Okay, then the last one under the structure of glucose is Hammond structure. Now to write the Hammond structure, first let's write down the cyclic structure of glucose. You have 6 carbon atoms, 1, 2, 3, 4, 5, 6. And then the first carbon is involved in bonding with the fifth carbon atom through the oxygen atom. And then you have OH, H, OH, H, and then OH, H, OH, H, and H, and then CH2OH. Now since OH is on the right hand side of the first carbon atom, this is called as alpha D plus glucose. Now if you want to write the Hammond structure for this, again this consists of a 6-membered ring. This also consists of a 6-membered ring, 1, 2, 3, 4, 5, and 1 oxygen atom. In this case also 1, 2, 3, 4, 5. So what happens is, this carbon is your first carbon, second carbon, third carbon, fourth, and the fifth carbon. 1, 2, 3, 4, and 5th. Now this 1 and 5th carbon atom are connected by the oxygen atom. Here also the 1st and the 5th carbon atom are connected by this oxygen atom. Now what happens is, whatever is on the right hand side of the carbon atom will come at the bottom. Right will go to bottom. Whatever is on the left will come on the top. Left on the top. Now let's arrange these groups. OH on the first carbon is on the right, so therefore OH on the bottom and then hydrogen on the top. In this case again, OH on the bottom and hydrogen on the top. And then you have hydrogen at the bottom and then OH on the top. On the fourth carbon atom, OH is on the bottom because it is on the right hand side and H comes on the top. Now on the fifth carbon atom, this CH2OH will always come on the top. And then this hydrogen. So this structure is called as alpha D plus glucopyranose. Pyranose because this structure looks like the structure of pyrene. Pyrene is a 6-membered ring where you have 1 oxygen atom and 5 carbon atoms. So that's why this name is alpha D plus glucopyranose. So if you take the structure of beta D glucopyranose, what happens is this OH will be on the left hand side. So everything remains the same. Only thing is you have to change the position of OH and the H. In the case of beta D glucopyranose, OH will come on the top, this hydrogen will come at the bottom. The dina bari chungor lana zo of cyclic structure ni Hemiacetal structure khande chungor ne. Khande chungor lana ta di na tana carbon check ni sum shi nga carbon nga ta oxygen check chine ring check na lo la chotwa ta shi di na lo la ge check ni sum shi nga chok yore check oxygen check sheba carbon nga di na lo oxygen check carbon nga ta di da la carbon thangbo ta ngawa ni oxygen gi tyore di na lo la ge carbon thangbo ta ngawa ni kare oxygen gi tyore ta di sama di na chotwa di chue la khari ta wona na eva chola do di khadi no di bond di wa che e chola do di khadi no wa do na di ka na tyore Dusini carbon thangbo gi OH di wala che ani e la do hydrogen di kare kala che dene carbon iwa ga OH di e la dwa di sine ko wala li re dene hydrogen di kala and dusini di hydrogen di wala che di OH di kala dure di OH di wala che di hydrogen di kala and khadi na di group chi dwa CH2OH di khadi na kare carbon ngawa gi kam de di re and di hydrogen di che those Hemiacetal structure. Now let me draw the beta D glucopyranose. Okay, in the case of beta D glucopyranose, you have OH on the left, hydrogen on the right. Now everything will be same, only thing is this position will change. So you will have this OH on the top. Okay, I'll just write it a different structure here. In the case of beta D plus glucopyranose, you will have OH on the top and this hydrogen at the bottom. Rest remains the same. OH, H, and then you have CH2, OH, and H. So this is about the difference between alpha D glucopyranose and beta D plus glucopyranose. Pyranose because it resembles the structure of pyrene. So when you compare the stability of beta D glucopyranose and alpha D glucopyranose, it is seen that alpha D glucose is less stable and beta D glucose is said to be more stable. The reason for this is in the case of alpha D glucopyranose, these two OH are closely with one another. Therefore, there is certain force of repulsion between these two OH. Because of which it is less stable compared to the beta D glucopyranose, in which the two OH groups have a good amount of distance between them. So that's about the Hemiacetal structure of glucose. So with this, we are done with the cyclic structure of glucose, open structure of glucose, and Haworth structure of glucose. And the biomolecules biomolecules and biomolecules carbohydrates, proteins, vitamins, nucleic acid and then carbohydrates 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 hydrolysis monosaccharides monosaccharides, oligosaccharides, polysaccharides monosaccharide the further hydrolyzed monosaccharide branch hydrolyzed monosaccharides and the oligosaccharides monosaccharides and polysaccharides. Monosaccharides के example glucose and fructose, oligosaccharides नामों sucrose, maltose, lactose polysaccharides नामों starch, glucose, glycogen. Those classification preparation of glucose consists of hydrolysis of starch or cellulose. Starch the cellulose nature glucose is hydrolysis glucose. Yana sucrose the fructose now glucose is co-hydrolyzed glucose and then structure of glucose monosaccharides structure the condense structure open structure, cyclic structure, and Haworth structure. And open structure the experiment then cyclic structure the condense and then Haworth structure. Those and and structure of fructose and disaccharides, polysaccharides. So in the next class, I'm going to do the structure of fructose and then disaccharides and then the polysaccharides. Thank you.